Evening, everyone. My name is Ellie Simmons, and I'd like to welcome you back to another Tech Talk in our series sponsored by Seismic. Today, we have the pleasure of welcoming Jason Stuhmer to give us a brief talk about load balancers. And without any further ado, I am going to go ahead and pass it over to you, Jason.
Great. Thanks for the introduction, Ellie. My name is Jason Stuhmer, and today we're going to be exploring load balancers and how they're used in modern applications. Before we dive in, I'd like to start by thanking Seismic for sponsoring this tech talk. Load balancing is more than just traffic distribution. It's a fundamental pillar of modern computing that keeps the internet running efficiently. So, what are load balancers? Load balancers evenly distribute incoming network traffic across multiple servers, optimizing resource usage, reducing response times, and prevent server overload. In high traffic scenarios, load balancing plays a crucial role in maintaining fast response times and delivering a seamless user experience. They also add a redundancy layer, minimizing the risk of single points of failure and improving overall system reliability. Before diving into further understanding how a load balancer works, let's explore some of the problems that can occur without a load balancer in place. There are three main problems with the model that's diagrammed on this page. The first is overloaded servers. Each server has a limit on how many requests it can process. So as a business expands and traffic increases, a server may eventually reach its capacity, leading to overload. There's also limited scalability as an issue here. Without a load balancer, simply adding more servers won't effectively redistribute traffic. Requests may still be directed to a single server unless additional configuration changes are implemented. There's also a single point of failure here. If a heavily loaded server crashes, the entire application becomes inaccessible, causing downtime. For e-commerce platforms, this results in lost revenue and a poor user experience, which service providers aim to avoid. So what does load balancing look like? You have a series of clients or users that are generating requests to a website or application. The load balancer acts like a middleman, sitting between the clients and the server pool, receiving the incoming requests. The load balancer distributes the traffic, deciding which server should handle each incoming request via several different methods and mechanisms, which we'll dive into shortly. Once the server processes the request, the response is sent back to the load balancer, which then relays it back to the client that made the original request. This seems much better. So we'll dive into a few different types of load balancing off the bat. The first is application load balancing, and then we'll proceed through network, global, and DNS load balancing. The types we have listed on this page are all correspond to different layers of the OSI model, which is the Open Systems Interconnection model. That defines how applications communicate over a network. Each type is designed for specific use cases. Higher layers, like layer 7, offer more advanced application-aware routing, while lower layers, like 3 and 4, focus on speed and efficient traffic distribution. Selecting the right load balancer, or a combination thereof, depends on your network architecture and your application complexity. The correct load balancer will help ensure optimal performance, scalability, and reliability. So first, we'll talk about application load balancing. ALBs optimize traffic distribution by directing different types of requests to appropriate servers based on their function. For instance, in an e-commerce application, browsing requests are routed to servers optimized for delivering images and videos, while shopping cart interactions are directed to servers designed to maintain persistent client connections and to store cart data. ALBs enhance efficiency by ensuring faster response times, balanced workloads, and better utilization of server resources. A practical example would be Amazon Elastic Load Balancer, which routes traffic to URL paths, enabling microservice-based architecture to successfully be implemented. So for example, your checkout endpoint would route to your checkout microservice. Next, we'll touch on network load balancing. NLBs are essential for real-time applications like massively multiplayer online games such as Fortnite or Call of Duty, which must potentially manage millions of concurrent players worldwide. They distribute TCP and UDP traffic across multiple game servers using predefined algorithms, ensuring low latency and high throughput. Designed for fast, efficient traffic handling, NLBs help minimize lag, prevent server overload, and maintain smooth gameplay experiences. Google Cloud Load Balancing is an excellent example of an NLB optimized for distributing TCP and UDP traffic in real-time applications like multiplayer gaming. The next type we'll touch on is global load balancing. Global load balancing is crucial for platforms like Netflix, which must run efficiently and deliver content to users across multiple regions, including USA, Europe, and Asia, for example. directs users to the nearest or least congested data center, optimizing latency, reducing congestion, and ensuring high availability. This is typically achieved using GeoDNS and intelligent traffic routing, dynamically balancing loads across geographically distributed servers. An example of this would be Cloudflare Global Load Balancing, which efficiently routes users to the closest regional data center to enhance performance and reliability. The last type we'll touch on here is DNS load balancing. So when a user enters www.google.com into their browser, their request must be routed to one of Google's many global data centers. DNS load balancing ensures that traffic is distributed across multiple IP addresses based on factors such as geolocation, server health, and network latency. If a data center becomes unavailable, the DNS load balancer dynamically updates records to redirect traffic to a healthy server, ensuring high availability and failover protection. This method is essential for global traffic distribution, minimizing downtime and optimizing response times for worldwide users. Google's public DNS load balancing is a prime example, intelligently resolving domain names to the most suitable IP address for efficient global service delivery. Load balancing can be further broken down into hardware-based and software-based solutions. First, touching on hardware-based solutions, these are dedicated devices that are specialized and designed solely to manage network traffic. Some key characteristics are that they are specialized hardware. They're purpose-built for efficient load balancing and high-performance traffic management. They have high throughput and are designed to process large volumes of network requests with minimal delay. They've built-in security features like firewalls and SSL offloading for enhanced protection, and they're very easy to deploy. They're dedicated devices, so they require minimal configuration and are generally very easy to set up. The benefits are that they're extremely fast because they have dedicated processors that allow for rapid traffic distribution, and because of the low latency, high throughput, and strong security features, they're ideally suited for high traffic enterprise environments. One potential drawback is these devices are very expensive, so upfront cost is heavy, and then expanding capacity also requires purchasing additional units, which also makes scaling costly. A few examples would be the F5 Big IP, the Citrix NextScaler, and the A10 Thunder ADC. Now we'll touch on software-based solutions. These are applications or components that operate on general-purpose servers. A few key characteristics that they're more cost-effective since they utilize existing hardware. They are scalable as well, horizontally by adding more virtual instances as needed. They're highly flexible in terms of their configuration. They can meet specific performance and traffic management requirements. They're also very easy to integrate, especially in cloud environments, making them well-suited for modern infrastructures. Some of these benefits are that they're highly scalable, they're more affordable, they're great for CI/CD pipeline compatibility and streamlined deployment. A couple of potential drawbacks are software overhead may introduce latency compared to some dedicated hardware solutions. They can pose an increased risk in terms of DDoS attacks and cyber attacks if they're improperly configured. And performance may vary because efficiency depends on the capabilities of the underlying network hardware and the network conditions. A few examples of software-based solutions would be Nginx, which is an open source web server software, HAProxy, which is a free open source software that manages traffic for HTTP and TCP applications, Traefik, which is an open source application proxy and load balancer that helps you develop and deploy microservices, and AWS Elastic Load Balancer, which is a fully managed service through AWS. So, how do load balancers achieve their functionality? They don't just distribute traffic randomly. They rely on specific algorithms to determine where to send incoming requests. These algorithms fall into two main categories, static and dynamic. Static algorithms distribute traffic based on predefined rules without considering real-time server performance, whereas dynamic load balancing algorithms make traffic distribution decisions based on real-time metrics like server health, response time, or workload. First, we'll jump into an example of a static load balancing algorithm. This is one of the most basic examples. It's called the round-robin algorithm. It's a straightforward static load balancing technique that distributes incoming requests sequentially across a group of servers in a circular fashion. Each request is assigned to the next server in line, repeating the cycle once all servers have been used. While this method ensures that requests are evenly distributed, it doesn't account for server load or capacity, meaning that a busy server might still receive new requests, even if it's already overwhelmed. The JavaScript implementation that I've got in the slide showcases how the round-robin algorithm might operate. So you've got a constructor function, which basically stores a list of servers and keeps track of the next server to assign the request. You've got your request handling, which is your getNext server function. Each incoming request is assigned to the server at the current index. You've got a circular rotation, which is established on line 16. So after a request is assigned, the index moves to the next server. And then you have your example execution down at the bottom of the code snippet, which outputs a log similar to what you have on the right-hand side. So you can see it just cycles through each of the servers that we have available, going from A to B to C, and then back to A again, and repeating until the requests are resolved. As far as use cases for this, it's best used for environments where all servers have similar capacity and can handle equal workloads. It does have its limitations, though, because it doesn't account for individual server load, and it's not really ideal for dynamic workloads where some requests require significantly more processing power than others. A couple of other additional static load balancing algorithms that you can explore on your own time are the weighted round robin and the source IP hash. I'll give a brief summary of each one. The weighted round robin builds on the round robin, but introduces weights to determine how many requests each server should receive. Servers with higher capacity, such as faster CPUs, more memory, or more network bandwidth, are assigned a higher weight, meaning they handle more requests than lower weighted servers. However, the cyclic distribution pattern remains the same as the standard round robin. The source IP hash requires or assigns incoming requests to servers based on a hash of the client's IP address. This ensures that users with the same IP source are always routed to the same backend server, which is crucial for applications that require session persistence or regional consistency. The next type of load balancing algorithm we'll jump into is a couple of dynamic ones. The first that we'll touch on is the least connection method. So this dynamically assigns new requests to the server with the fewest active connections at any given moment. Instead of distributing requests blindly, this algorithm considers real-time server load to prevent congestion and improve efficiency. This ensures that no server is overwhelmed while others remain underutilized. Unlike round robin, which follows a fixed pattern, least connection adapts to active workloads, making it particularly effective for environments where the request durations vary. The JavaScript implementation in the slide showcases how the least connection load balancer might operate. So similarly to before, we have a constructor function, which this time, instead of just storing a server list, it also tracks the number of active connections. And handling the requests, this also finds the server with the least number of active connections using the reduce method, and then signs the newest request to that server and increments its active connection account or count. It releases connections as well and tracks that, and it simulates that request completion in this particular example by decreasing the active connection count when a request is finished. So in the example execution, you can see I'm using a math.random function to simulate the end of requests just based on a random order. So you can see in the output, the requests are being handled in a completely different order from the round robin. You're getting 2 in a row routed to server A, then followed by B, then C, then back to A, then 2B, then C, then A, and A again. So this efficiently handles requests in a more dynamic way, and it's ideal for applications with variable request durations, such as video streaming or large file uploads, where some connections remain active much longer than others. A couple other additional dynamic load balancing algorithms are the least response time and the resource-based. So the least response time algorithm prioritizes fast request handling by routing traffic to the server with the quickest response time. Instead of distributing requests randomly, this approach monitors and analyzes server response speeds in real time, ensuring low latency processing for users. It continually measures how long servers take to respond, adapting its routing logic to direct traffic to the fastest and least overloaded machine. The resource-based load balancing method allocates traffic based on real-time resource usage, such as CPU load, memory consumption, or network bandwidth. Instead of relying on static weights or past data, this algorithm dynamically evaluates server capacity before assigning new requests. It ensures efficient resource utilization by preventing requests from being sent to overloaded servers while maximizing available system resources. Load balancing is such an interesting facet of modern internet technology because it's everywhere. Every time you stream a video online, you make a purchase, you play a multiplayer game, load balancing is happening in the background. Global giants like Google, Netflix, and Amazon rely on sophisticated load balancing techniques to serve millions of users without any downtime. It strikes a balance between simplicity and complexity. It starts with simple strategies like round robin, but advanced methods involve AI-driven traffic management and real-time health monitoring. It's a field where both fundamental and cutting-edge techniques coexist, making it accessible for beginners while challenging for experts. It also solves real-world problems by preventing server overload, reducing latency, and ensuring system reliability, which directly impacts user experience. Whether it's handling Friday traffic surges for an e-commerce site or managing real-time video streams for a live concert, load balancing plays a critical role. It also blends software, networking, and cloud computing, so it connects multiple disciplines. It adapts to emerging technologies. With AI and ML, predictive load balancing is becoming much more common, automatically adjusting traffic based on usage patterns. It's also a high-stakes game because a poorly designed load balancing strategy can crash a website, slow down a service, or cause revenue loss. In contrast, a well-optimized system ensures seamless scalability, high availability, and lightning-fast performance. You can see my works cited attached if you'd like to dive into this some more. Unfortunately, I ran a bit over this evening, so we're not going to have time for questions. However, you can feel free to reach out to me via email or LinkedIn if you'd like to explore this topic further. I'd like to thank Seismic again for sponsoring this Tech Talk, and I'll toss it back to you, Ellie.
Thank you so much, Jason, for that really, really informative talk. Thank you so much, everyone, for coming out tonight. We will see you at the next one.